So IONQ has been around a while. One of the things that needs to be said about this space is that most of the work is being done by the bigger companies like IBM, Google, and others. It doesn't mean a small company can't succeed. You have to look at the pure plays, because if you buy Google, you're not really getting huge exposure to quantum computing. Maybe you're getting a little. IBM is a little bit different, and we can look at IBM as well. I'm gonna put these in hardware, maybe semis or electronics and computers. I don't know, maybe semis. They're not even semiconductors though. Kind of a futuristic computing. All right, so IONQ is a $7 stock. Like I said, they went public through a SPAC, which is like typically a not so exciting. Okay, QBTS, there's another one. You want me to look at that one too? Might as well. And so one of the things I do when I'm looking at a kind of like a general space is I want to make a spreadsheet for the general space. Yeah, you can actually rent Rigetti, IONQ, and maybe we'll do that today. Maybe that'll be fun. We can rent one of these computers, including IBM. You know, obviously some people make qubits through superconductors. Certainly there's a way to, you know, if there's a supply chain that makes sense to analyze, we can do that too. But let's just like flip through the IONQ 10Q. They've actually got some pretty smart people at IONQ, even if they've had limited success. I like this glossary. When have you seen a glossary in a 10Q or 10K? An algorithmic qubit is a metric describing a number of useful qubits in a system, considering noise, connectivity limitations, and other sources of error. So why don't we make like a little, and again, all these files get saved to my GitHub. If you haven't seen my GitHub, go to github.com/Martin Shkreli, and you can download all these files yourself. So I'm just gonna write some of the definitions here. And again, some of the stuff I know pretty well, some of it I don't. So this is kind of like the key thing about quantum computing that I think is not well understood, basically, is that you basically have this gigantic entanglement of quantum states, and then you have this period of measurement or observation or whatever you want to call it, where you get an output and the entire coherence collapses into one. A lot of times these days, really important new technologies don't really matter to the stock market because most of the good companies kind of stay private and stuff like that. I do think quantum makes SHA-256 obsolete and ECC obsolete. And in fact, we'll do some integer factorization. What does quantum mean? Great question. That's the kind of place I want to start at, and then we build our way up to the top. So quantum basically means the word quantize. It appears all over the world. It appears in music, it appears in chemistry, it appears in artificial intelligence. To quantize means to take something that is traditionally thought of as a real number, in other words, a number with decimals, like 6.3 or pi or 7.5, 1923, some real number, and turn it into an integer. And so quantizing basically is this idea that there is a finite limit of precision, that at bottom there is a number that will act as a unit. In music, you could think of it as a 64th note. There's no shorter note than a 64th note, if you so deem. In AI, we can quantize the weights of a neural network to 4 bits, or 8 bits, or 1 bit if you'd like. And all the weights have to be represented that way. The interesting thing about where the idea of quantum, which is the unit we're talking about in quantum mechanics, came from, well, we can, you know, ask ChatGPT or go through history, but there's this guy called Planck, and he kind of came up with this idea that you could actually have energy that's emitted in this specific amount, and we call it Planck's constant. And again, I'm not a physicist or chemist, so this is little tough to me. But you know, I like to learn, and we're going to try to learn together sometimes, right? This idea prior to Planck, and you're talking about over 100 years ago at this point, that you can irradiate some substance and how much radiation it's emitting. I don't think we're going to get to multiverses anytime soon. The amount of energy emitted has an absolute minimum. this idea before is that maybe it's continuous, right? And this is one of the most important mysteries in physics is here's a distance, whatever distance this is, right? Maybe it's 5 feet, okay? Well, if I cut this distance in half, we know that each one of these is 2.5. And basically the question is there an amount that I can cut where I can no longer cut anymore? At some point, is there a block, I can take this and zoom in, and there are two schools of thought here. Either that matter is continuous, or it's discrete, or quantized. And the same applies to time. Is there, if this were 5 seconds, it would be the same question. And we don't have an answer. Does God give us a resolution the same way we have 640 on our monitors, or at least we used to? Do we have a resolution for the universe? Well, we know in the Planck experiments that there was a resolution, that there's a discrete amount of energy that could be emitted, and it's a very small amount, but now it's called Planck's constant. And that's where the idea of a quanta, it's just like fixed amount of energy. You cannot have half a quanta. It doesn't work. It's a specific amount, and each time a particle emits energy, it does maybe 1 quanta, or 2, or 4, or 3, or it's a specific amount. Discrete just means non-continuous. So that's what quantum means. And basically, why is this important? Who cares? Well, there are a bunch of other interesting kind of things that come around here. The idea of quantum mechanics is that these, at that quantum level, where we're measuring things in that quantum, that small amount, that things behave very differently. The world is very different at that small level. It's like in the macroscopic world, where Newton's laws prevail. In the quantum world, things are very strange. It's not like what we're used to. And we have to think about basically a different kind of physics, and we call it quantum physics. And it's one of the most mysterious, somebody's mentioning it's reality shattering. It's true. It's one of the most mind-blowing, wild, ideas in the history of mankind. And for a while, people just didn't think it was true. And one of the most important ideas is Schrodinger's work, with particle wave duality, which is kind of a quantum concept because we're dealing in the quantum size. And that idea is that particles and waves are the same thing. And a particle can be more wave-like, or a wave can be more particle-like, depending on its size. I think everyday people can understand quantum mechanics. I will tell you that it's not for the faint of heart. In our channel and in our community, we've built a very special collection of people. And some people stay here for a year or two, and they go on and do their thing. Some people stay forever. But over the last 10 years, I've been streaming, and there was about 5 years in between there where I couldn't stream. I've seen a lot of people who are curious, who come in and they want to learn, and they want to extend their knowledge as much as they can. And I know I'm not a physicist at all. I'm nobody. And we strive to understand things the best we can. And a lot of these people have ended up becoming billionaires, CEOs, both. Some of them didn't. But we pursue knowledge as vigorously as we can. The approach that I take is this very sort of basic, start with the fundamentals and then work your way up. Quantum computing is this idea that can we take advantage, and it sort of started with this guy, Richard Feynman, who's a good Brooklyn guy like me, where how do we take advantage of the universe's quantum properties to do computation? And what's funny is we used to try this, and we had a field actually called analog computing. And this was we talk about this a lot in my Discord and other places like that, where we had this field of analog computing where people would use wood or screws or whatever to represent bits. And then we moved kind of to the transistor, right? We forgot about we forgot about analog computing. And the question is there a better way than transistors to represent states? And with analog computing, we forget about the discrete binary system. We go back to a real and continuous system. And so we can represent all kinds of fractions of numbers. And in fact, that's kind of what we do in quantum computing. And I would argue that quantum computing is a form of analog computing. there's a number of other analog computing ideas. This new one called thermodynamic computing, which I'm part of this movement called 𝐸AC, which stands for effective accelerationism, and thermodynamic computing. There's a few companies pursuing this idea. But really, to me, it's all just back to analog computing, where it's this idea that, in essence, the simple fact is that instead of working on zeros and ones, we can work on the continuum. We could have 0, we could have 1, and we could have anything in between. And by leveraging this, we can get an exponential amount of compute, theoretically. I think, at best, quantum computing will be like GPUs in like the first few decades of GPUs, where it's just used as a coprocessor. Like we used to have algorithmic coprocessors. So I think there's like a lot of ways to sort of handle this. But Alan Turing a long time ago used to make analog computers very briefly to calculate Riemann sums. So could you design an analog computer to say factor 2 numbers or something like that? There's a lot of interesting ideas. I don't think quantum has much to do with pharma, to be honest. I know some people want to believe. It remains to be seen. If you could do really good simulations, perhaps. Again, this company uses kind of these ion traps to make a qubit. You can kind of use anything to make a qubit. So I think that we're going to see how different companies approach different attempts to make qubits. We've got transmon, superconducting qubits. We've got all kinds of ideas. All right, so let's look at how IONQ at least describe themselves. We're developing quantum computing. Quantum computers designed to solve the world's most complex problems. We sell quantum computing hardware together with maintenance and support. We sell access to several quantum computers of various qubit capacities, and are in the process of researching and developing technologies for quantum computers with increasing capabilities. So what we're often going to see is this number of qubits, and it kind of matters and it kind of doesn't. We'll kind of go into that. So they are connected on AWS, Azure, and GCP. And they also have their own cloud service. IDEA, computing, the greatest invention of all time, Moore's law, etc. It says here in their own words, quantum computing uses information in a fundamentally different way than classical computing. Quantum computers are based in qubits, a fundamental unit that can exist in both states simultaneously, a superposition. As a result, we can address problems that classical computing may never solve. This is a bit of a misleading definition, but it's the common definition of quantum computing. It may be able to represent all that information for a very small amount of time. So it's kind of like the classical idea in computing of a time-space trade-off, just in a new quantum way. And if you believe in space-time, it kind of makes sense. Simulation of quantum systems, number factoring, complex optimization like traveling salesman problem or 3-SAT or whatever. You can't do these on a classical computer. Maybe you could do them on an IONQ computer. So we need more qubits. The success will require more qubits than our current computers. We will be able to find these solutions and overcome these challenges. There are thousands, if not millions, of important unanswered questions about how the universe works, and quantum computing will answer them. All right, so what are they doing? They are constantly kind of creating more and better quantum computers. They have 9 generations of prototypes, which is kind of funny. They sell through the cloud, and they sell direct access. For certain customers, I think they'll actually sell you the computer itself. But they also do quantum computing as a service. And yeah, it's basically based on Maryland. And we'll kind of meet their chief scientific officer from there. Quantum simulations in chemistry, Monte Carlo, optimization, quantum machine learning, lots of ideas there. But what are the challenges? Basically this idea of a quantum advantage or quantum supremacy, which I think people maybe don't like that word, is when a quantum algorithm can beat a classical algorithm. And we'll look at some of the kind of key papers of, I see somebody knows bracket notation. I think probably quantum computing has a place in high frequency trading. And yeah, we're early in quantum computing, to make no mistake about that, but you could have been early to biotech too. So it makes sense to watch it at the very least. So the physical system of qubits must be nearly perfectly isolated from its environment to store quantum information. In fact, you're going to read about how IONQ once didn't understand why they were getting noise in their readouts, and there was actually a truck that would go by their office, and the truck caused the problem. So even light, any kind of light, everything has to be shielded. We're going to talk about quantum gates. We're going to look at this very interesting kind of way to notate that looks a lot like music. It looks like staff. It's a good question, Mark. The dilution refrigerator, I kind of wondered what companies make dilution refrigerators, because you have to... Actually, it's a really good question, Josh, because like, can you put quantum computing in space? You know, there's very little noise out there, right? I'd rather kind of do it up there. Just send it on one of those Dragon rockets or whatever, and you know, it's pretty cold up there. You don't need to do too much cooling, and there's no noise. I mean, there's going to be some gamma rays and stuff like that, but you can shield that. So yeah, let's. Do you guys want to buy a dilution refrigerator? What is this, like $1 million? You've probably seen this before if you've seen pictures of quantum computers. It all kind of revolves around this dilution refrigerator. So I need to get below 10 millikelvin. I want to get even lower than that. I want to say it's around $2 million, but I could be wrong. Who are these guys? Bluefors. Who is Bluefors? Millikelvin. Imagine we get to like microkelvin. Holy moly, look at the revenue. 15 years, and they've got to 190 million revenue. Wish I could have bought that stock. We got another company making them. Let's see. Let me try price. Okay, 500K to 2.5 million. Well, you know, you're talking about cooling a small part of space near absolute zero. So like, what is that, 237.5? Do you guys remember? 273. Got a little dyslexia there. 273.15 negative 273.15 degrees Celsius is 0 Kelvin. So even 1 degree higher would be way too much. So we are trying to get to 0.0001 Kelvin. And basically the amount more zeros we can add, the better. At these temperatures, nothing moves, right? There's no entropy. Everything's frozen. And this is a very small amount of space. You know, so that big fridge, this is not drawn to scale. That big fridge, it looks like a chandelier, doesn't it? The amount of space that's being cooled to that level is so small. I always wondered, like, well, does it make the whole room cold if it's that cold? And the answer is no, because the amount of space that it's cooling is extremely, extremely small. I always wondered, well, if you put my hand in there, will I get frozen or something? So yeah, you need, in general, that kind of state. Could you have a room temperature quantum computer? It's possible. If you can't get it at those low temperatures, it won't work. So we're going to go into that, and we're actually going to, like, if we have time, I have no problem paying for and renting a quantum computer right now. But let's see how fast we can kind of understand what's going on. So they have to be isolated, precisely controlled, measured with high accuracy. So its basic computing steps have to be there with low error rates. And one of the problems right now is that what we're going to see is that these computers aren't really useful or practical right now because they can't do things that you're any better than what your computers can do now. So your laptop or desktop, whatever you're watching this on, even your phone, is probably faster than a quantum computer right now. But the proof of concept is important because if you've proved that you can make it, what that means is even though you're dealing with, you know, this is like general compute here. And we've gotten to like this point, arguably, and this is arbitrary numbers, of course. Quantum computing is sort of the same curve, but maybe steeper, and maybe we're here. So it doesn't feel great to be here when, oh, I can just do this on my classical computer. Well, one thing is like maybe the classical computer curve is a sigmoid, where it's going to start reaching an asymptote. And in fact, you know, NVIDIA would tell you that that's exactly what happened. And that QC is the only way to continue Moore's law. And again, NVIDIA has something to say about this. Yes, and we'll go through the quantum supremacy newspaper, paper in Nature. I had this, I read this in jail, and a lot of the guys were saying, Martin, what do you got there? What's so interesting? And I said, this computer costs, $10 million or $100 million to make. And the guy leaned over and said, can I steal it? I said, well, if we plan the operation, we'll have to sneak into Google. And they said, well, how do we sneak into Google? I said, well, we're going to get some passes, and we're going to act like we're Google guys. And then we're going to take the Dilution refrigerator and walk out with it. And he said, easy. This guy was one of the most famous bank robbers in the country. He said, any security or guards? I said, not really. You'll be fine. So mission impossible, right? AI is way more important than QC. QC is just a way to... Dense computing is what made deep learning possible. So we don't really know what's possible if we could get another step function compute, which would come from quantum computing. But I'd say if you ask Jensen Huang what he thinks about quantum computing, he's probably sitting there saying, why do I need quantum computing when I'm doing the fastest compute in the world? And I don't see a bottleneck. I'm going to keep going. It's like a Grand Theft Auto mission, right? Choose your driver, choose your break-in guy, choose your Google guy that you corrupt, and bring the quantum computer to who exactly? Who's going to buy that? I think Moore's law is maybe accelerating, which is kind of crazy. It's not holding up, it's actually getting faster. But let's stay focused, because I do want to get these done. Okay, so we mentioned that this idea of being able to store information, process the information, all these like traditional things you do in computing have to be applicable here. The quantum computers here are based on individual atoms. So think about how small that is. A 100 qubit system, we're talking about 100 atoms. If you know Avogadro's number, the mole number, you think about how many atoms are in a mole of carbon. A mole of carbon isn't very much. Really a huge amount of atoms possible. Natural quantum bits. So these are natural bits, or natural occurring substances. So photon is an idea. Even in atoms, we have ions versus neutral species. A lot of the properties, I guess, could be used. Kind of interesting, right? Does photon have spin? Does a photon have spin? I think it's got a set spin, +1 or -1. So you could use that as well, I guess, probably. Spin in semiconductors, sometimes called spintronics. This is solid state quantum computing. And then we've got superconducting qubits. And you can actually simulate a quantum computer with regular old computer desktop software. In fact, we can make sure our software is right before we rent the quantum computer. What's amazing about these quantum computers is that it takes just 1 second to do the computation. You don't have to sit there like with the GPU. We have programs that run for weeks. With a quantum computer, you press the button and it's done. Before you can even... So their idea is that atoms are nature's qubits. And I think that's right. That is the right approach. I like ion trap. QCs can't be used for mining Bitcoin yet because they're just slow. They don't have the speed required. So one theory here is that it might take 1,000 physical qubits to form a single error-corrected qubit. But right now the ratio is 16, closer to 16 to 1. Ion trap. So if you have 1,000 qubits, physical qubits, 5 or 6 real qubits. Coherence is 10 to 50 microseconds versus longer time, potentially for an hour, as much as an hour for ion trap. So that's kind of interesting. So they're just talking about how great ion trap is. So you use lasers to move the atoms. I don't know if a quantum computer would solve the Riemann hypothesis or not. DoD is very interested, so is NSA. Okay, so I'm excited enough. Now I want to get to when do we get to use it?